Assalamualaikum and hi. Our group 6 with the title of Flow over Immersed Body and Boundary Layer Theory. We consist of 3 students. My name is Amirul Azim Izainuddin, Matric ID MA18122 from section 6. We start the presentation by presenting our brief background and theory. Louis was the first to propose the idea of boundary layer effects in the early 1900s. Although the general fluid equation had been known for a long time, their solution did not adequately explain observed flow effects such as wing stalls, and Louis was the first to note that the magnitude of inertial and viscous forces change as you move from a layer near the surface to an area further away. He first suggested a two-layer interactively coupled approach that accurately models several flow problems. The phenomenon is known as boundary layer when it occurs. Aerodynamic forces between the fluid and the object are produced in this boundary layer. The drag and lift forces are the two most important aerodynamic forces. The boundary layer is depicted in the diagram below. And the drag and lift forces are characterized respectively as these two formulas. Problem statement of this project is, for blunt bodies like a sphere, an increase in surface roughness may cause a decrease in drag. The transition to turbulent boundary layer flow occurs at a lower Reynolds number than for a smooth sphere. One effect is that the wake region behind the sphere becomes considerably narrower and overall drag is reduced. The objective of this experiment is to design complete measurement technique for fluid flow and measure the drag and lift forces applied on a symmetrical aerofoil at different angles of attack. Next, to determine for rough and smooth surfaces the velocity distribution and boundary layer thickness of a flat plate subjected to a longitudinal flow. And the third objective is to determine a full fluid flow measurement technique and experimental method, as well as the drag and lift forces applied to a symmetrical aerofoil at various angles of attack. The scope of this project is similar to a circular cylinder. The inviscid flow field around a sphere can also be determined analytically. Velocity distribution in the laminar boundary layer over the front part of a sphere can be calculated using a series expansion technique. It requires, however, an experimentally determined pressure distribution if accurate values of skin friction and boundary layer thickness are to be achieved.
Masula bin Abu Bakar, and my ID is MA18126. So today I'm going to continue to present about the experimental setup and the procedure. So in this experiment is consists two different experiment, which is experiment 1 and 2. So for experiment 1, the crucial things that consist in this setup is the airflow bench, smoke controller, manometer, aerofoil model, and the radial fan speed controller. While for the experiment 2, the crucial things that consist is the manometer, rectifier, and the pitot tube. To the procedure. So first, for procedure 1, experiment 1, the first thing that we need to do is we need to set the initial height of the manometer. After that, the angle of the aerofoil need to be set to 0 degrees. This is because it's to allow the air to flow into the chamber. Then the fan speed was set to 12 and the blower was turned on. This is because to allow the fog into the flow, into the chamber, and then the fog machine was turned on and the fog button was pressed intermittently. The fog streamlines pattern in the aerofoil chamber was being observed and sketched. After that, the height of the manometer was measured. Then we need to observe the change in the flow patterns, and then the fan velocity was gradually increased. This step from step 3 to 7 need to be repeated at 45 degrees and 30 degrees of angle of attack. Next is for the procedure for experiment 2. The first thing we need to do is, before we beginning the experiment, the manometer's initial reading was registered. Then in the airflow bench, a flat plate with a rough surface was mounted at the 20 mm radius. Then the pitot tube was balanced with a vernier calipers until it was almost touching the plate surface. Then the reading gauge needle was set to 0 as it is starting point. The airflow bench was turned on and the vernier caliper was changed by 4 mm increments until the manometer height was stable. For every 20 mm increase in flat plate distance, the manometer height was recorded. Then we need to repeat this step from 1 to 5 with a higher y-axis value until we reach 140 mm. And then lastly, we using a flat plate with a rough surface, we need to repeat step 1 until step 6. I think that's all for me. Thank you.
Hi everyone, I'm Yuneshwari from Group 6. Today I'm going to present about the results and graph for Lab 2. In this lab, we have conducted 3 experiments, that is flow pattern of symmetric effort at different angle of attack, experiment 2A smooth surface plate, and experiment 2B rough surface flat plate. In the first experiment, we are given angle of attack in 0 degree, 30 degree and also 45 degree. The streamline of the effort at different inclination angles with separation and stagnation points can be seen in the figure. Experiment 2A, that is smooth surface flat plate. The initial height is given as 274 mm. From the given data, that is height, we have found the velocity for the smooth surface flat plate. So to find the velocity, we use the formula velocity equals to 2g delta h square root. Basically, delta h equals to h initial minus height recorded from the experiment. Moving on to the next Reynolds number, the formula used is velocity times by distance of the plate divided by kinematic viscosity. This is the graph shows that we use the 10 mm plate reading for height, velocity, Reynolds number for smooth plate surface. The experiment 2B is about the rough surface flat plate. This calculation also have been done as same as the previous one. We have obtained the Reynolds number, and also this is the graph same using 10 mm plate distance for height, velocity, Reynolds number for rough surface plate. For the discussion, experiment 1, basically the lift coefficient and drag coefficient is proportionally proportional to the dynamic pressure and area. And the second experiment, we tend to investigate regarding the flow of air in smooth and rough flat surface. The experiment, we calculate the velocity across the boundary layer thickness. The manometer height decreases because boundary layer thickness increases. This explains that the dynamic pressure increases across the boundary layer thickness because the differences between the initial height and measured height gets increased. Finally, about the conclusion, in the experiment 1, we have able to conduct the lift and drag coefficient directly proportional to the lift and drag force. In experiment 2, the velocity of air flow has clearly affected the boundary layer of the smooth rough surface plate. So that's all from us. Thank you.